Hello everyone, welcome back to my channel. Today we are going to go over this problem of fluid mechanics. So let's read through the problem. Workers at a construction site need to remove water from a deep hole that is greater than 15 meters deep using a pump and hose. The first attempt to remove the water involved placing the pump at the surface of the hole and lowering the suction side hose into the pit. Unfortunately, this approach was unsuccessful. Another worker stated that the hose was too steep using this approach and that it would be better if the hose had a gentle slope, as shown in figure 2. That approach didn't work either. A is why did neither of these approaches work? And B, what should be done to remove the water from the hole? So, um, basically, the problem with both approaches is that they rely on atmospheric pressure to push the water through the hose from the pit to the hole surface. And atmospheric pressure can only support a, a specific height of column of water. And after that height of water, it cannot support any more, which means that it will not be sufficient pressure to do the job. So how do we calculate the height of water that atmospheric pressure can support? We calculate it from the hydrostatic pressure distribution. So like this is what it looks like basically um basically we we can have like a device that helps us to measure the pressure. And basically over here we have the vapor pressure of water, which we will call PV. And over here, this will be filled with some amount of water. And um, the water or liquid, and the water is pushed until that height. And P atmosphere is over here. So P atmosphere is the only pressure acting on the water, pushing it up to a height of, let's call it H. And P atmosphere can only push the water up to this height H, but not more. So how do we calculate height in terms of the atmospheric pressure and the vapor pressure of water? Well, P atmosphere by Newton's second law, which is like all forces must balance each other in the vertical direction, all forces must balance each other. That means that the force from the atmospheric pressure must equal to the force from the vapor pressure of water plus um, the the pressure from the height of the water. Because atmospheric pressure pushes down on the water, which translates to an upward force over here, acting on the water and the vapor pressure. But the vapor pressure and the pressure of the weight of this column of water acts in the opposite direction. It creates an opposite force. So these two forces have to balance each other, since force is related to pressure, because pressure is equal to force divided by area. So essentially, we're saying that the atmospheric pressure must equal the vapor pressure of water plus the weight of the column of water, which is rho, the density of water, times gravity times the height of the water. And we can rearrange this equation to get that P atmosphere minus PV, the vapor pressure of water, divided by rho G is equal to height of the water column. And now we plug in typical values of each of these. So the typical vapor pressure of water um, at 15 degrees Celsius is equal to 1.706 kilopascals. Oop. And this is absolute pressure, not gauge pressure, which means that it is not relative to the atmospheric pressure. It is the absolute pressure. And absolute pressure, the definition of that is the total pressure at a given point measured from absolute zero. Um, and gauge pressure is measured relative to atmospheric pressure. Um, Let me see. Yeah, gauge pressure is a measurement of pressure in a system relative to the ambient atmospheric pressure. It represents the pressure difference above or below atmospheric pressure. So, yes, now we have the vapor pressure and we have to know the atmospheric pressure. The atmospheric pressure is equal to uh 101.3 kilopascals. And this is absolute pressure, of course, because we're measuring absolute pressure relative to absolute zero. But the gauge pressure of atmospheric pressure will be zero since gauge is relative to atmospheric pressure, and atmospheric pressure relative to itself is zero. Rho is the density of water, which we take to be 1,000 um, kilogram per meters cubed. And basically, gravity G is equal to 9.81 meters per second squared. And thus, plugging in these values, we have that the height is equals to 101.3 minus 1.706 uh, all over 1,000 times 9.81. And calculating this, we have that the height is equal to 101,300 pascals minus 1,706 pascals over 1,000 times 9.81. And this is thus equal to a height of 10.2 meters. And our conclusion is that thus it is not possible for atmospheric pressure to push the water a height of more than 10.2 meters because fluid moving through a hose will reduce this height further because there are also pressure losses associated with viscous forces in the hose, which will counteract the flow of water. And a longer hose will increase these pressure losses and reduce the maximum height even further. And therefore, the scenario in figure 2 is even less effective because the hose is longer. And in order to remove the water from the pit, the pump should be lowered into the pit so that the pressure applied at the exit of the pump is larger than atmospheric pressure. And the more powerful the pump is, that means the larger the pressure rise across the pump, the higher the water can be pushed. Thus, for depths more than a few meters, it's almost always better to put the pump at the bottom of the pit, so the pump can generate a large pressure for pushing the fluid upwards. Basically, what has to happen is that our pump in the pit has to be placed like this, and it has to be able to push the water out like such, and the pressure here is greater than atmospheric pressure. And basically the water covers the pump and it is at a height of 1 meter and at a height of 15 meters. So yes, all the numbers stay the same. Yeah, and basically this height is 15 meters. And yes, basically this is the configuration needed to remove the water from the hole. Um, and thank you for watching this video, and I hope to see you guys in future videos. See you next time.